All right, let's take a look at some of what Spark SQL can do. And there's a lot. We'll only be covering the basics, a small portion of what's capable here. The first thing to note is the core point of a Spark SQL program, the SQL context, is just a wrapper around the regular Spark context. In Spark 1, it was available directly in the shell via the variable SQL context. However, in Spark 2, when SQL became non-experimental, it was wrapped in a Spark session, propagating a number of SQL context starting point methods, and became the default starting point, created via a Spark session builder in standalone applications. It's now automatically added as the Spark variable in the shell. As we're focusing on the SQL side in this section, we'll work directly with the session's SQL context, which is really a Hive SQL context, just one abstraction level higher, providing all the same functionality plus a little extra. So, you may run into access problems if you try to use SQL in multiple shells at the same time. Now, before we begin, we have some setup. First, we'll import some SQL implicits to help make the Scala code a little nicer. However, as before, I'll point out where and how this is used so that you can create the equivalent Java code. Notice that the implicits are based off of the SQL context itself, which this implicits object was only added in 1.3. If you use a version before that, then to get the same functionality, you'll need to import everything from the SQL context. With our implicits loaded, we'll need to create a company class, which we'll use for part of the demo. Company is a case class, which is useful as it's automatically serializable for our function passing, but it also extends the product trait, and we'll see why this is important shortly. First, we have to create our list of companies. Once created, we can use it to create our first data frame using the toDef method. This is made available through our implicits object, where the sequence is passed into SQL context's createDataFrame method and then wrapped in a holder object, which at that point merely returns back the created data frame. This is where the case class and its inheritance from product comes into play. The createDataFrame method can use reflection to determine the data frame column information if this product inheritance is in place. Otherwise, you'll need to pass in a second parameter containing either a pre-built schema object or the Java Bean class. And Spark's distributed nature stems out of RDDs, so of course you can create data frames from your RDDs just as you can with sequences. Now, if we want to take a quick peek at our data, we can call the dataframe's show method to print the first rows, or you can optionally pass in the number of rows you want displayed. But what about loading data from source? Well, as of 1.4, you simply call SQL context's read property, which provides you with a data frame reader, which contains some methods for common data source types, such as JSON for loading JSON files. But it's dynamic enough to be able to load non-built-in formats, passing your file type into the format method and calling load. And if your format isn't a file, then you can build the necessary key value information through option methods. Note that I said this is only in 1.4. Prior to that, you'd use very similar methods, but calling them directly on the SQL context object. And it should also be noted that, pertaining to JSON, the default JSON reader will not work for multi-line JSON objects, only working with files that contain one entire JSON object per line. However, in Spark 2.2, the multi-line option was enabled to alleviate this pain point. Next, let's take a look at another nice thing about data sources and Spark SQL, and that's SQL's ability to dynamically figure out schemas for a number of data sources. In fact, using the DataFrame method printSchema, we can see that when our JSON file was read in, the correct schema was indeed inferred. This alone is a really nice way to quickly grok the metadata of something like a new, complex JSON format, instead of having to open and sift through a mess of JSON. However, this schema inference does come at a price. Unlike our RDD loading methods, the SQL loading methods run immediately through as much of the data source as is necessary for it to figure out the schema. Now, since our original in-memory data frame has the same schema as our JSON file, let's try to union them together. That didn't work. Even though they both have the same company metadata, notice that the order of our inferred schema doesn't line up with our case class data frame, as well as the inference engine took the safe approach and inferred our integer column to be a big int. So, we can fix that by re-projecting our columns through the data frame's select method. The $sign is making use of the string to column implicit class, which converts our string into a column object. And column has a number of convenient helper methods. We'll only see a handful, but it's definitely a good place to look and see the kinds of operations available against Spark SQL columns. Here, we're using the cast and as methods to cast our big int down into an int and make sure that the final name of the column shows up as employee count. Although, admittedly, the naming is for aesthetics. Only the column order and types matter for automatic schema merging. Our union method will simply opt to use the calling data frames names. After the type negotiation, we simply rearrange the columns to match our case class structure. And take note that if we had only needed to rearrange columns, then we could have used simple string names to reference them without the $sign conversions, which would be compatible with Java, whereas the $sign notation is not. So, after successfully merging our data frames together, we can take a look at how to get access to this column class in Java. Here, we'll take our company data frame and group it by whether it's public or not. Even though, again, we could just use the string name for the column, we'll pass in the column object. This is done by using the data frame's call method, which takes in our column name as a string and passes back the column object corresponding to that data frame's column. And that's how you can gain access to the data frame's column object in Java, which, in Scala, could have been simplified even further by removing the .call and referencing the column directly on the data frame. This would use the data frame object's apply method behind the scenes. This means of referencing the column is especially useful when joining with other tables, as it disambiguates one table's column from another's column. Now, once the data frame is grouped, we can aggregate through our group data object via the ag method, passing in a list of at least one aggregation expression. Here, we're averaging the number of employees so that the end result is the average employee count at our public companies and the average at our private companies. And while this works in the Spark shell, in a standalone application, you'll need to import all from org.apache.spark.sql.functions to use these functions, like avg or sum or max, or a number of other such functions. But once imported, this really does make aggregation fairly simple. Okay, we've seen projection and grouping. How about filtering? Here, we're using the more SQL-like where operator, but could have just as easily used the filter method, which where is merely an alias for. This is pretty straightforward. We're taking our employee count column and filtering down to any company with more than 1,000 employees. And as Java doesn't have the ability for operator-like methods, the equivalent Java is to first get the column through the data frame, as we just saw, and then use one of the operator alias methods. Here, the greater than operator aliases to the GT method. And there's one other alternative. we could have written out the query in a string and just let the analyzer handle it. Now, what about once you're done processing and ready to save the data? You can use the write property, which exposes the DataFrame writer class, similar to the DataFrame reader we use to load our data. Again, this class has a JSON convenience method built in, but could be set through formats and options just as before. So, all of these DataFrame methods are pretty nice, but sometimes Spark SQL can be too restrictive. In those cases, we can just drop out of data frames into the RDD level, as we know that data frames are backed by RDDs. But the immediate objects behind data frames are rows, which are similar to arrays of any's or objects in Java. So, when dropping down, we'll first need to convert from a row to a more statically typed object. Here, we're using row's apply method to extract column values via index and casting them to a known type. In Java, you can achieve the same thing by explicitly calling the object's apply method. And in Python, you can access the object via square brackets as you would any other collection. Alternatively, the row class has getString, getInt, a number of other get types, or a getAs type generic method that combines the extraction and casting actions into one method. However, the simplest transition comes in Python, where you can actually access the row columns by name due to its dynamic nature. And coming back to DataFrame to RDD methods, this map is merely an example, as a number of RDD operations are made available directly on the DataFrame object. Or there's an RDD or Java RDD property to extract straight into an RDD of rows. This all makes it easy to go back and forth as you feel fit. And one final note on this front is that, once again, I highly suggest following up this course with the follow-on, Handling Fast Data with Apache Spark SQL and Streaming, as it covers the Typed Dataset API and more, where the Dataset API brings that RDD feel to this SQL-tuned backing.